So in the second part of the lecture, we will develop the Hodgkin-Huxley model for neurotransmission in terms of the nonlinear Hodgkin-Huxley model. Now, before we try to develop some equations, let's first look again back on the phenomenology of the experimental results and find some electrical explanations. The first is that we see that there are conductances which are running in parallel. Now the curve that has been measured on the bottom left is nothing like an IV curve where we look on the change of the current as a function of the voltage. So this is a typical experiment that you do. And for regular resistor, what you would expect is that the IV current in that case is just linear. Now if you have two parallel resistors, what will happen is that the line just will get steeper, as indicated by the dashed curve. Now the membrane not only consists of parallel resistors, but also has internal batteries, which are the Nernst potentials of the different ions. So the effect of adding an additional battery into your electrical scheme is just that you shift the linear IV curve on the x direction, depending on the membrane potential that you assume. And then the line just crosses zero voltage, zero current at the membrane or Nernst potential that you apply. You see also nicely that the experiments on the bottom left follow such a trend. You see, if there's no sodium current, we just have a linear line, more or less. If we switch on the Nernst potential of the sodium, we see a shift of this line, and it crosses at plus 45 millivolt, which is the Nernst potential of the sodium. Now, in the earlier clip, we proposed that there's some nonlinearity happening in the resistance, meaning that the resistance now gets a function of the voltage. Let's assume we have such a resistor, here indicated a resistor with an arrow, which is a sort of a potmeter. And let's assume that at a certain switching or gating voltage, UG, the resistance switches from a high value to a low value. Now in such an IV curve, the IV curve that you would expect in this case is that you have just two linear relationships, so two lines, where the steepness of the line switches at UG. This is a little bit what you see at minus 15 millivolt, what is happening at the high sodium concentration in the graph bottom left. Now, if we further assume that this switch from one resistance to the other is not a steep switch, but it's somehow gradually changing from one to the other, you could easily imagine that this will lead to some smooth curve that much better reflects what you see in the experiments at the left. Now let's put this a little bit into equations. So here you see again our model. So it's the typical Hammond cable, but now with changing resistances, Ga, G sodium and G potassium. Now the sodium conductance is equal to 1 divided by the sodium resistance, and that is given by the current through the sodium of the sodium ions divided by the membrane voltage U minus the Nernst potential of the sodium UNA. Now likewise for the potassium ions, so GK is equal to the current of the potassium ions divided by membrane voltage U minus the Nernst potential of the potassium ions. Now, in order to include the switching, we include the non-linearity in the resistance. For the potassium ions, the resistance of the potassium gets now voltage dependent and is equal to the resistance of the sodium without the without the switching behavior, times 1 plus beta times U minus the gating voltage squared, where beta is just some prefactor that tells how much the resistance will change. Now, putting this into the membrane current, so we can now calculate the membrane current, is then equal to the membrane current of X and T is equal to the voltage at X and T divided by the resistance of the sodium ions times 1 plus beta V minus V gating squared. Now to the right you see about what the different behavior that you would expect. So first we look on the sodium conductivity, and you see it switches from a low value to some high value. And to the right you see the membrane current, and you see right away from the equation, this is a third order equation in the voltage. So it will have 3 crossings of 0 and 1 maximum and 1 minimum. Now this description we now take and plunge into the linear cable equation. The linear cable equation was basically the equation given by considering the different currents flowing along the axon and through the membrane. There we found that this we can describe by a second order differential equation where lambda squared times the second derivative of the voltage with respect to space minus tau times the first derivative of the voltage with time is equal to the voltage. Now, because we changed the description here, we have to multiply that expression with the nonlinear expression of the resistance, then leading to an extra term reading 1 plus beta times V minus V gating squared. Now it's easier to rewrite this last equation, knowing that a third order equation will always look a little bit like the curve on the top right. So we have 2 local extrema and 3 crossings through 0, which determine typical voltages V1 and V2. And the expression that we here obtained can be re-expressed in those terms, leading on the right-hand side to a term V times V minus V1 times V minus V2 divided by V1 and V2. Now we are interested in to solve this nonlinear equation, differential equation, yet with an important constraint. Namely, the question that we were asking is whether this nonlinear equation allows for a traveling wave solution. Now, a traveling wave solution would be a solution where the voltage at position x and t can be described by a reduced voltage or an average voltage, which does not depend explicitly on x and t, but on a traveling wave solution, which looks like t minus v divided by theta, where theta is the speed of the wave. Now, the speed of the wave will be described by the ratio of lambda, which is the typical length scale, and tau, which is the typical time scale. Now, filling in the real numbers of real axons, we will find that the speed, typical speed that we would expect, is in the order of 1 meter per second, which actually is the speed that is observed in experiment. Now, keeping this in mind, and that we're really after a traveling wave solution and not a very general solution to this complicated equation, we now define a reduced time, which is s, which is equal to t minus x divided by theta. By that, dt is equal to ds, and the dx will change to minus theta ds. We now get a second order differential equation, which only depends on this reduced time variable, reading lambda squared divided by theta squared, second order the derivative of dv by ds squared minus tau times dv by ds is equal to v times v minus v1 times v minus v2 divided by v1, v2. Now, let's remind you again, we are interested in whether there is a wave-like solution to the differential equation, and we don't want to really calculate the solution that will come up, which probably will be very complicated. Now, it's again good to go to reduced variables, which basically takes away all the units that are implied in the v hat and so forth. So first we define a variable y, which equals minus theta divided by lambda times s. Again, a unitless number. Then we find q, which is theta divided by lambda times tau. Further, we define some reduced voltage, V tilde, which is V bar divided by V2. And we have an additional parameter which relates the two crossings of this third order equation given by V1 divided by V2. Now, using these abbreviations, we obtain now a second order differential equation which reads like second order derivative of v tilde divided by dy squared is equal to minus q times dv tilde by dy plus p times v tilde to the power 3 minus 1 minus p v tilde to the power 2 plus v tilde. Now we see again at the last part, this is a third order equation in v tilde. Now it might seem unintuitive to do so, but it's a good idea to think about that this relation we could also assume to be a potential. A potential in the way that this third order equation is equal to du by dv tilde, where the u is a potential which is a fourth order, which is in fourth order of the reduced voltage v tilde. Now, in a pictorial way, this fourth order equation would somewhat look like this, where actually the first term has to be negative. Hence, I do have a potential which goes to minus infinity at both ends in V tilde, but it will have two maxima and a minimum in between. Now, further realizing that the first term could be a friction term, then what we end up with is basically a harmonic oscillator, including friction, which is living in a potential well. And the solution will basically describe the movement of the system between these two maxima. So as a summary of what we learned is, in principle, we could solve this differential equation, but it suffices us for the time being that we realize that the system looks like a damped harmonic oscillator that is placed in a potential, and that will lead to a solution that allows a stable traveling wave in the axon. Now that we know that there is a traveling wave solution, let's look into even more detail of the behavior of the system. And there in particular we look on the conductance of the potassium that has been measured, and we look on the switching behavior of the potassium ion after activation as a function of time. What has been shown experimentally is that there is a rising phase. It goes from a low value to a high value, and then dropping off again to a low value. Now, people have been trying to model the increase and also the decrease of this current. So the experiment that has been done is you can describe now the current of the potassium ion as a function of the voltage minus the Nernst potential of the voltage, and you get a mean value for the conductance times a factor which should include the time behavior of the switching. Now, what has been found for the activation is that n, the activation part of and the time behavior, can be described by an exponential, or actually it's a 1 minus an exponential with a typical timescale tau activation A. The same also holds for the inactivation. So the n for the inactivation would be n infinity times e to the power minus t divided by tau inactivation. Now, if you look on a little bit more detail, you will find that in the activation part, this simple equation, the 1 minus an exponential, is not sufficient to explain the behavior. And what you need is you need to lift this to a power of 4. So there are two independent units. So the idea behind this model is that there are 4 units that can either switch on or off independently, and only if all 4 units switch at the same time, the channel is completely open. Likewise, the description you obtain for the sodium conductance, where the sodium current is given by the resistance, typical resistance of the sodium ions, times U minus the Nernst potential of the sodium ions, times activation term to the power 3 times an inactivation term H. Hence, in total, the current through the membrane is now given by the addition of the sodium, the potassium, and some leak current, and given by the equation that I show here. So the total current is equal to m to the power 3 times h times the conductivity of the sodium ions times U minus U sodium plus n to the power 4 the conductivity of the potassium ions U minus U potassium plus some leak conductance U minus the leak potential. Now, those kind of the values for M, H, and N have been found by experiment like on the left, where you look the response of the different currents as a function of time at different applied voltages and voltage steps and at different concentrations of sodium or potassium. So the information of the inactivation you obtain by an experiment where you give pulses, 2 pulses at short interpulse distances, and then look on the direction of the action potential, and you will find that there is a gap between which the current cannot be changed anymore, and the ion channels are inactive. Now, putting all this together, so the Hodgkin-Huxley model and the Hermann cable, we can obtain the experimental results using the model that we developed.